G'day guys, and welcome to this whole new chapter on reviewing algebra. Yes, those of you who, as usual, are being taught by me, you have the joy and pleasure of doing all of those questions. Thank you so much. But we're going to do a bit of a recap of all the things that you're about to learn or that you already know to be able to master this particular topic. So algebra is one of those things that I actually call obligor. Why do I call it obligor? Because generally speaking, if I say to kids, oh, we're about to do algebra, you will go, groan, not again. And then sort of your brain sort of shrinks and goes, nah, not going to learn any more of this, didn't understand it last year, not going to understand it this year, which is not true. Actually, for each year you age, your brain actually gets far more developed, and surprisingly, you will find stuff easier if you give it a chance. So as we can see here, we are looking at the terms, no pun intended, of term, coefficient, equation. You need to be able to know what collecting like terms is. What about the difference between simplifying and evaluating? The distributive law. Now, I don't know about you, but I tend not to teach specifically the distributive law. I don't think I've ever used that word in my classroom, so that might confuse people if a question ever says, use the distributive law. And then there's this factorizing and substituting malarkey, which we will come on to a little bit later on. So this lesson, if you already know it, skip ahead to the next one. If all of that stuff, you're like absolutely positive, I know this stuff, brilliant, move on. Now basically, let's start with a term. A term is something that has a collection of numbers and letters which might be multiplied together. Now, what do I mean by that? Well, here's some examples. So 3 plus 4. They're actually two terms, believe it or not. Why? Because this is one term and this is another. Anything that's separated by pluses and minuses is generally a term. What about 2a? That's a term. Plus 3b. That's a term. Plus 4c. That's a term. Plus 5d. That is also a term. Now, terms can have any collection or any number of things multiplied together. And there are some tricks, basically, that I'm going to show you in a moment. So 2a, b, c, d plus 3a. They are two terms. You notice that between all of these things is a times. Now, I never call it a times. I actually call it a kissy. And you're going to say to me, Darren, have you lost the plot completely? Well, generally speaking, yes, that's why I'm sitting in a room on my own talking to myself. But if you look at my cards that I send to my mum and dad, I will, for Mother's Day, which is coming up in Australia, which is completely the different day from the UK. And sorry, Mum, that I missed your Mother's Day this year. It completely flew past me. I had no idea. But at the bottom, I put something like love, Darren, and then kiss, kiss, kiss. Well, surprisingly, what do we see between this 2A, B, C, D? There's two kissy, kissy A, kissy, kissy B, kissy, kissy C, kissy, kissy D. And as far as I'm concerned, those things there are all just kissing each other. Way too bad a mental image, so we won't get too excited about that. But yes, that there is a term. Now, one of the tricks we use, and please be very careful with this one, is this. If I had 3 brackets A plus B, believe it or not, that's also a term. These brackets here curve around the A and the B, and they effectively say, treat me as one thing. And so between the 3 and the A and the B, or the 3 and the times, the 3 and the bracket is a multiply. And when everything is connected together, then that is a term. So if I had 3 bracket A plus B plus 4 bracket C minus D, how many terms have we got there? Well, hopefully every single one of you are screaming at the screen, two terms. And yes, because that bracket basically says treat me as one thing, and that bracket there says treat me as another. Between the 3 and the bracket are timeses, and so this is one term and that is one term. Now that comes in much later on into maths, but if you can understand that concept, it's going to help you with things like factorizing and simplifying and all sorts of different things. So what about this coefficient business? Well, the coefficient, as I say here, is a term. A coefficient of a term is simply the number in front of that term. It's the number. So if I had 3ab, this number 3 is the coefficient. It's the number in front of that term. If I had 6a squared d, oh look, I put a squared in. Again, this is still a term. Doesn't matter that it's got floaty numbers or powers or indices, depending on which you want to use. But this value here, this 6 is the coefficient. They don't all have to be positive. Minus 7 bracket a plus b all times c. Hold on a minute. What's that dot thing you're saying? Well, that dot is actually shorthand for times as well. Wow, we're doing a lot of stuff in this coefficient stuff. Well, let me just do a little aside. If you had something like 7 times x times y times z times x, what do you notice about your timeses and your x's? Well, they look very, very similar. Now, in the pressure of an exam, imagine if you'd written out all these times x's and then suddenly you just had a brain burp and you mistook those timeses for an additional x's. Well, your answer is going to be completely wrong. Well, we generally speaking in mathematics use a dot to signify that it's a times. And you're going to tell us, well, hold on a moment, that dot means a decimal point. No. Very big difference. You'll notice that the dot here is actually on the line. If I wanted to do a decimal number, the dot is very definitely between them. Right? Subtle difference, but very important. And a word of advice to all of you, make sure you do your x's with a curly C or the sort of backward C and a forward C. If you had your x's with normal timeses, yeah, you have no chance, right? So, and examiners, believe it or not, are looking for x's to be like this. All right, I say back to coefficients. So this value here is my coefficient, -7. Swiftly moving on, equations and expressions. What's the difference between an equation and an expression? Well, an equation basically has an equal sign. That's it. An equation has an equal sign and is generally something that you can then go on and quote-unquote solve. In fact, I'm going to write that in quotes. Solve. All right, so what do I mean? Well, if I had 3x plus 4 is equal to 13, for example, that there is an equation. It is something that I can solve, but it also is something that equates one thing to another. So that and that are equal. They are equivalent. They are equations, or an equation in this case, with a very French accent. Thank you very much. As you can see, here I would be able to take away 4 from each side, which would give me 9, and so x would be 3. I can find a specific value of x because of that equal sign. An expression has no equal sign and is generally something that can't be solved. In fact, it's probably something that can't be solved. What do I mean by that? Well, look, if I had 3x plus 4x minus 2x, that does not have an equal sign. So it is an expression. I can make it look simpler because we know that we can collect like terms, which is, funnily enough, coming next. So 3x's plus 4x's, 7x's minus 2x's gives me 5x. I haven't actually found what x is, but I have simplified it that I might be able to go on later in a question and actually solve or use that to help me solve for x. So remember, equations and expressions, one has an equal sign, equations, and one doesn't. Collecting like terms is actually strangely exactly as the English says. Like terms are terms that are alike. Now we already know a term is something like 3a and 4a and 6b and 9b and 7xy and 12xy and 14x squared y and 17, I don't know, xy squared. Ooh, spot the odd pair. But the point of these is now 6 of these are, or two, there are 3 pairs that are like terms, and then obviously 1 pair that isn't. Now, as I say here, we can't collect bananas and bananas together. When I go to Coles and walk around with my supermarket trolley or my little basket to try to buy fruit, if I'm going to buy apples, then I will buy apples. If I put apples in my basket and then more apples in my basket, I can add them together and go, oh, I've got more apples. I've got 12 apples. But if I put apples and bananas in my basket, then I'm not going to turn around and say, well, if I put 3 apples, say I put 3 apples in my basket and 4 bananas, then I'm not going to suddenly turn around and say I've got 7 apple bananas. They don't become, just because the apples and bananas are in the same basket, we don't actually have to segregate them. We don't turn around and go, no, apples and bananas shall not live together. And also I have to be very careful that I don't believe that they're actually in my basket doing, strangely unmentionable things to become an apple banana. There is no such thing. So generally speaking, funny enough, I tend to think of these things as apples and bananas and, xylophones and yaks and all sorts of things so that I can make sure in my head I can add them together. So in this situation, I could collect 3a and 4a together. And collecting basically means adding or subtracting, depending on what the question is asking you. So 3a and 4a is 7a. That's collecting if I was adding them together. I can do 6 bananas and 9 bananas to give me 15 bananas. Getting hungry again. Now, in this situation here, doesn't matter how many letters you've got, so long as they are exactly the same. So in this situation, I've got xylophone yaks and xylophone yaks. I have no idea what that looks like. It could be a yak playing a xylophone. Random, but this is the way my brain works. 7 xylophone yaks and 12 xylophone yaks is 19 xylophone yaks. Now, if we look at this one here, they cannot be collected together. And you're going to try and say, well, hold on a moment, they've got an x and a y in them. They do, but they have square x's in that one and square y's in that one. Now, you're going to try and say, what's a square apple? Right, well, this is it. Think about 6a and 6a squared. They are not the same. And I think to myself, well, that is like 6 apples in my basket, and that is 6 square apples. Now, obviously, apples normally are nice and round, but square apples would look odd. So I can't add those together because they are not like terms. And because the squared belongs to the x here and the squared belongs to the y there, I can't add those together. So all sorts of examples could be used, but there are plenty for you to be going on. Now, as I say here, the tips and tricks which are used, and these come up ever such a lot in maths, is this. If I had 12x squared y plus 10xy squared, as I've just said a moment ago, they cannot be added together. Why can't they be added together? Because the squared belongs to the x there, and the squared belongs to the y there. So that's like saying 12 square xylophones and a yak, and 10 xylophones and square yaks. They don't even sound the same, so I can't possibly add them together. But what about this? Now, if I had 12 apple, banana, and carrots, and 3 carrot, apple, bananas, then are those together? Well, the first thing is you can see the word cab there, and you're going to go, oh, cab, or Uber, lol, 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 lol. But maths is going to try and trick you. So if I had 6xy plus 3yx, are they the same? Absolutely they're the same, because there's 1x and 1y, 1x and 1y. Order when you're multiplying is not important. Think back to 1 times 2 times 3. What does that equal? 6. What is 3 times 2 times 1? 6. What is 2 times 1 times 3? Hopefully 6. And I could keep moving that 1, the 2 and 3 around. So long as they are all multiplied together, it doesn't matter what my order is. And at exam, they will try and trick you. Now, you know as well as I do, we tend to write the number first in a term and then all of the letters in alphabetical orders. But exams aren't going to be there to be nice to you. I've said here squares, cubes, and mores. Maths being a big fat trick. Again, 12x squared y plus 12yx squared. Are they the same? Of course they're the same, because although the order is different, I've got a square x, a yak, and a yak. So I can add those together to give me 25 now. X squared y. Lots of people, I'm sure, think that when you add square yaks and square yaks, you get yaks to the power of 4. No. When you multiply, you do. But when you add, it just stays, right? So if I have 12 square apples and 6 square apples, just imagine putting those into my coals, right? 12 square apples and 6 square apples must be 18 square apples. It is not 18 apples to the power of 4. I wouldn't even know what that looks like as an apple. Right? So again, maths uses these type of tricks, and if you haven't worked them out previously, now is the time to do so, because in year 10, it's critically important that you get algebra sorted by the end of this year, because methods 1 and 2 and 3 and 4 uses it a lot. Right? So again, just say out loud. If I was to say this out loud, it'd be 12 square xylophones and a yak, and another 12 square xylophones and a yak. I don't have to pronounce it this way because they're all times together. Just one last thing, it's not always plus. So if you have 9a squared plus 2a plus 3a squared minus 4a, for example, let's collect like terms there. Well, I've got square apples and square apples, which are added together because this plus sign here always belongs to the thing preceding it. So 9 square apples and 3 square apples gives me 12 square apples. 2 apples minus 4 apples plus 2 apples minus 4 apples would be minus 2 apples. And then we could probably go on later and factorize that, but let's not rush. Difference between simplify and evaluate. Basically, simplify means collecting like terms. Simplify, exactly as the wording says, make things look simpler, but not necessarily find a final answer. As in, if we look here, simplify 3a plus 4a, hopefully all of you now know that's 7a. Can I then use that information to go on and find a? No, we don't know what a is because they haven't given me an equation. Congratulations. This is just an expression. Evaluate means exactly that. And generally speaking, it means find an actual numerical answer. So this is where we're going to solve something. And what do you notice there? We've got that equal sign in. It's an equation. And so basically, 3x equals 12, so x must equal 4. Yay, thank you very much. Simplify doesn't just have to mean adding and subtracting. It can include multiplication and division. So if I had 4a times 3a, now, we'll come on to this much more a little bit later on, but 4a times 3a. And actually, when things are multiplied together, I can rewrite them. So because that's 4 times a times 3 times a, putting those kisses back in, and because I remember that 1 times 2 times 3 is the same as 3 times 2 times 1, which is the same as 2 times 3 times 1, and then on, then generally speaking, when things are all multiplied together, I move all the numbers together and do that first. Well, 4 times 3 is 12. And then a times a is a squared. And so 4a times 3a becomes 12a squared. And if I had a division, which would be 16a squared divided by 4a, for example, well, I know that's the same as 16a times a divided by 4 times a. Now, we'll come back to all of this in a bit. But I know that 4 goes into 16 4 times, and I know that an a on the top and an a on the bottom become 1 on a 1 because anything divided by itself. So 4 times 1 times a gives me 4a, and 1 times 1 gives me 1. So there we go. So simplify can also be used for that as well. The distributive law is used to basically expand brackets. Now, you've been expanding brackets previously in year 9, and I imagine at some point in year 10. But just be careful that when you expand brackets, if I had minus 3 times a plus b, then when you use the distributive law, everything outside the bracket gets multiplied by what's inside the bracket. And I always draw those arrows. So minus 3 times a gives me minus 3a. And minus 3 times plus b. Well, minus and a plus becomes a minus, and 3 times b becomes 3b. Right, so expanding brackets is just multiplying what's outside the bracket by what's inside the bracket. And this can become even more complicated. Easy for you today, say, Darren. We've got like 2 sets of brackets there. Well, what we do is we draw a dotted line between them, and we basically consider one part of the sum at a time. So I'm going to look at this section first. I'm just going to multiply out because the 6 belongs to that set of brackets. So 6 times a, 6a. 6 times plus b, plus 6b. So that's the first bit done. Now I'm going to move on to this second section. So, but remembering that that is a minus 2. So the minus belongs to the 2. Really, really important. So minus 2 times x is minus 2x. And minus 2 times plus 4 is minus 8. Can I now go on and collect like terms? Well, sadly not. Are there other apples to go with my 6 apple? Nope. Are there any other bananas to go with my 6 bananas? Nope. Are there any xylophones to add on to my minus 2 xylophones? Nope. And this number here, remember, this is just a number. It's not an apple. It's not a banana. It's not a carrot. It's not a dolphin. It is just an 8. And so if I had other numbers on their own, I could simplify or add those together, but I can't. All right, so look, I've even jumped the gun. I've even done that already. My goodness, my brain is working ahead of me. So I don't need to use that space. I'm just going to move on. Actually, no, I'm not. Remember the 4 important rules here. Minus times a minus, positive times a positive, plus times a plus, or a minus and a minus become positive, and a positive and a negative, and a negative and a positive become a negative. Now, if you don't know what that is, go and sort it out. Look back. Finally, factorizing. Oh, no, not finally. I've got substituting into equations. We're already at 19 minutes and 28 seconds. My goodness, what's going on with this lesson? Factorizing is awesome, all right? And it's used ever such a lot in mathematics, like hugely in mathematics. Now, basically, when we're using factorizing, we're doing the opposite of the distributive law. we are taking outside of a set of brackets what is common to both terms. Now, there's a better way of thinking about it. We are taking outside of a set of brackets the maximum that we can divide out of both terms. And you're going to go, what? Let me give you an example. If I had 4a plus 8, for example, how many terms have we got? We've got 2 terms. Marvelous. So here is my first term, and here is my second term. That should be a 1. Okay, so what am I now saying? Well, do each of these share a number? They do. The first term has a 4, the second term has a plus 8. They have a coefficient. What's the biggest number we can divide into 4 and 8? Well, hopefully 4. So I'm going to move outside a set of brackets, the number 4. And I'm going to leave a space for the moment, because having dealt with the coefficients, we then look at the term, the rest of the term. Do they share common letters? Well, while this first term has an A in it, this second term just have a number. So there's no common letters. I'm done. So we're now saying I've got to end back up with 4a plus 8 when I multiply this bracket out. So I'm dividing. So 4 times what gives me 4a? Well, hopefully a. 4 times what gives me plus 8? Well, hopefully plus 2. And ladies and gentlemen, you have just factorized. You have taken outside of a set of bracket the biggest thing that can be divided into both of those terms. Let's do another example. 6ab plus 18b. Ramping up the complexity. How many terms do I have? I have 2 terms. All right, thank you very much. So I can factorize this. Let's look at the coefficients first. We've got the number 6 and the number 18. What is the biggest number that divides into both 6 and 18? Well, hopefully 6. So that's the coefficients dealt with. Now we look at the letters. Are there common letters that appear in both of them? Well, absolutely. In this situation, the letter B appears in both of them, but letter A doesn't. So we can't take any A's outside my brackets. So remembering, we've got to end back with 6AB plus 18b when we multiply out this bracket, because this is just the opposite of the distributive law. 6b times what gives me 6ab? Well, the only thing missing was the a. 6b times what gives me plus 18b? Well, 6 times what gives me 18? Well, plus 3. And the b has already been moved outside. So actually, 6b times 3 gives me 18b. And there we go, ladies and gentlemen. That is my final answer. That is my factorized form. And last example, where I've got my space. Let's do it here. If I had, I don't know, think of something. 16a squared bc plus 8ab squared c. Same thing, you're looking for the maximum we can move outside. Right, so always look at your coefficients first. 16 and 8. What's the biggest that can move outside? It's 8. Now look at my letters. I've got 2 a's here. Now you're going to turn around and say, but that's a squared. It is, but a squared is the same as a times b times c. And this here is a times b times c. So how many a's do they share? Well, this has got 2 a's and this has got 1 a. And the most I can take out then is just 1 a. I have to take out the biggest I can for what they share. How many b's has this got? It's got 1 b, but this has got 2 b's. Well, it doesn't matter. We can take out only 1 b then. And what about the c's? This has got 1 c, this has got 1 c, so I can take out my c. Draw my set of brackets. Remember, we are trying to get back to 16a squared bc plus 8ab squared c. So 8 times what gives me 16? It's got to be 2. A times what gives me a squared? It's got to be a. And the b and the c are already outside, so that's good. I don't need to worry about multiplying inside my bracket. 8 times what gives me 8? Well, plus 1, so we won't worry about that. A times what gives me a. Then I've got 1b outside, but I need 2 b's. So I'm going to plus b. And I've got 1c outside and 1c. So again, this here is my factorized form. It's used ever such a lot in maths. Substitution. When you think about footy, what do you think? Well, substitutions of left, right, and centre is pretty knackering out there, or pretty tiring outside when you're running around. So we can assign letters with numbers and actually make this so much easier. So here's an example. If I've got the equation 3a plus b divided by c, and I tell you that a is 2, b is 3, and c is 4. When you substitute, everywhere you see an a, you're going to put 2. Everywhere you see a b, you're going to put 3. And everywhere you see a c, you're going to put 4. So if I just follow that to the letter of the law, that becomes 3, 2 plus 3 over 4. So 32 plus 3 is 35. 35 divided by 4. And hopefully all of you are going, no, 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 stop. And I am stopping. Huge mistake here. Yes, when you substitute in the numbers, you replace the numbers with the letters or the letters with the numbers, but you have to remember that 3a is the same as 3 times a. So actually, if I was to have substituted this in properly, it would have been 3 times 2 plus 3 over 4. So 3 times 2 is 6 plus 3 divided by 4, and that becomes 9 over 4, or 2 1/4. Always be very, very careful. If I'd had this as 3 brackets a plus b on c, then I'd have to again have gone 3 times brackets 2 plus 4 divided by c, which is 4. Work out the brackets first. 3 times 6 on 4, 6, 12, 18 on 4, which gives me 4.5. The questions above are going to have you practicing all of these type of skills. I'm done. 26 minutes and 29 seconds. Wow. But there was a lot of stuff to recap. Practice makes perfect. Thanks very much for listening. I look forward to seeing you next time. Thanks so much for joining us for that video. It was really good having you. Now, if you'd like to know when the next video is coming, why not click on subscribe? Alternatively, head on over to MaffsGuru.com where you can watch all of the videos on its own dedicated website. Otherwise, watch the video that's just popped up. It'll be part of this series. All right, take care. See you again soon.